Hi, good morning, everybody. My name is Marius Sokolewicz, and today I will be talking about the use of remote sensing techniques and numerical modeling to predict coastal erosion in Vietnam. I will start with the context and research topics of our study. Then I'll move to case study in Quang Ngai City in Vietnam. I'll talk about the remote sensing techniques for prediction of coastal erosion, which we used. I'll compare different techniques and discuss selection of best performing technique. Then I'll talk about numerical modeling, the conceptual model of coastal erosion which we developed, then how we predicted future development of the coast, and I'll end with conclusions. All materials presented here originate from a large World Bank funded investment planning study aiming to increase resilience to coastal hazards in Vietnam. We studied hazards at 6 locations along the coast of Vietnam. I have selected for today one of these locations, the coastal district Quang Ngai City on the central coast in the picture below. The coastal zone here is located near the outlet of a large river, Chaco, with a size comparable with the Rhine. The adjacent coast suffers from severe erosion problems which we investigated in our project. In the erosion assessment, we studied the historical erosion, studied natural processes driving this erosion, and starting from there, we estimated future erosion to inform regional planning. Our study had to deal with very limited information. Luckily, we could use the freely available satellite images to verify official disaster reports and witness accounts of the damage after the recent catastrophic typhoon Damri. Our erosion assessment was mainly based on remote sensing and numerical modeling. We had access to a large collection of Landsat images covering a period of 35 years. These images have a resolution of 30 meters. Since 2015, more accurate images with a resolution of 10 meters are available from the Sentinel-2 missions. A huge advantage of these both types of images is that they are freely available from internet sources like Google Engine. An alternative with commercial high-resolution images would be very costly. They cost about $1,000 per image, and we needed tens of images for our study. Recently, several methods have been developed to automatically extract shoreline position. AquaMonitor internet tool from Lutares to start with. Within Royal Haskoning DHV, we have developed our own tool. And recently, open source tool CostSat is becoming increasingly popular. On this slide, I have compared these three methods. They are all based on the same theoretical concept, the normalized difference water index, which is a method to detect the land-water boundary. Each method uses a slightly different version of this index. AquaMonitor uses only the Landsat images. The other methods use both Landsat and Sentinel. The output of AquaMonitor is the annual shoreline change based on analysis of all images from that year. Other method extracts shoreline's position for each separate image. All methods can be used to detect long-term change, but AquaMonitor cannot be used to detect more frequent changes on a timescale shorter than 1 year. When dealing with shoreline detection, it is very important to keep in mind that the position of the waterline varies during the day with the tide. A difference of water level of 1 meter on a 1 in 50 beach gives a difference of 50 meters of the waterline position, which could be wrongly interpreted as erosion. AquaMonitor averages the tidal impact out by taking many images. In our own tool, we select images to be at similar water level, for instance, high water. In CostSat, we used our own extension to perform the tidal correction according to the astronomic tide and the beach slope. Okay, and now let's talk about the results. We have selected 3 transects north of the river mouth for comparison of results of these 3 methods. In this figure, we can see that all the methods give quite similar results, which gives confidence in the correctness of the result. CoastStat uses many more images, and this gives a larger scatter. This scatter is, however, within a range of 30 meters, similar to the image resolution. There is no reason to give preference to one of these methods. When looking at the actual results, we see that the shoreline change trend varies in time. Until 2003, the coast was accreting. Then there was a period of 10 years of relative equilibrium, and from 2010, the trend changed to erosion. We see similar trends in the other transects. Close to the river mouth, there is more dynamics, probably due to a stronger interaction with the estuary. The different methods show similar patterns, but they are based on the same theoretical concept. We looked for an independent method to verify these results. We found that the high-resolution images in Google Earth are very suitable for this purpose. They don't have an exact timestamp, so the shoreline position is not directly comparable because of the unknown tidal effect, but the vegetation line is independent of the water level, and vegetation retreats with the retreating shoreline. The retreat of vegetation line is a good proxy of the actual erosion. The retreat of vegetation line is 10 meters per year, which is very close to the satellite-based erosion rate, which confirms the correctness of the results. So we established the historical erosion rate, but we also wanted to know how much erosion could occur during a severe storm. We set up a typhoon model and modeled a 1 in 100 years typhoon and used the wave heights as input to the beach evolution model. We found that the beach and dune could retreat by 30 meters during this storm. We compiled all those insights into a conceptual model of coastal behavior. We understand that the coastal dynamics is strongly related to the dynamics of the Chaco River outlet. This outlet is very active and changes with the season. During the dry period, the flow is not strong enough to push out the river sediments to the sea, and a sandspit is forming. During the monsoon, the flow is very powerful and opens the outlet, largely removing the spit. Sediments feed the littoral transport. The last decade there has been a lot of sand mining up the river. This explains the ongoing coastal erosion. The goal of this assessment was to give an estimate of potential future erosion to inform the district's planning. The future coastline will be affected by the erosion trend, but also by the sea level rise. The impact of sea level rise was estimated using an empirical rule of Brun at 15 meters retreat in 50 years. The future erosion risk zone was then defined as the sum of storm erosion, erosion due to present trend, and the sea level rise impact. This zone close to the river mouth could be as large as 550 meters in 50 years. This is based on a very crude and conservative assumption that the present erosion trend would continue unchanged for next 50 years. We consider this acceptable for planning purpose, as it gives a clear message to the authorities that this is an area of significant risk. A recent development in AquaMonitor is a function to estimate future shoreline change. It is interesting that AquaMonitor predicts 5 meters per year accretion, while we found 10 meters per year erosion. This is due to the fact that AquaMonitor disregards the trend changes, meaning that the results need to be treated with caution. And finally, the conclusions. Automated remote sensing methods of shoreline prediction provide indispensable information for planning purposes, but a good understanding of the coastal system is essential. Trend analysis and numerical modeling help to build this understanding. And an important lesson is do not rely blindly on automated predictions. Human factor is still of crucial importance. So this was all. Thank you.